when you look at a question like this, what is it that we're looking for in terms of isotopes, atomic number, atomic mass? And charge is the third thing we'll be dealing with a little bit later. But what does atomic number, what information is given by the atomic number?
The number of protons and neutrons.
Is that the atomic mass or the atomic number?
Oh.
Because there's a difference. One of them is bigger than the other one. So which one do you think is both protons and neutrons? All right, we'll put you down. There you go.
The number of the electrons.
Is the atomic number?
The electrons.
Okay, that is true only for neutral atoms. So if that's the case, if the atomic number is equal to the number of electrons only in neutral atoms, what do you think the atomic number actually refers to?
Is it the number of protons?
It is the number of protons. Yeah, you have to remember, so that is the number of protons. Because the number of protons defines an element. That's the only thing that defines an element. It's just the number of protons. The number of electrons defines the relative charge of an atom. If there's more electrons than protons, it's going to be negatively charged. And if there's fewer electrons than protons, it'll be positively charged, but it's still going to be the same element. It'll just have a different charge. What about the number of neutrons? What does that change? I can have the same element, but with different numbers of neutrons. So what does that change?
Does it have to do with the isotopes?
It does have to do with the isotopes. So if I have, yes, so the same element can have different number of neutrons, and they're called isotopes. But if I increase the number of neutrons in an element, what number does that also increase?
The mass.
The mass, exactly. So the atomic mass indicates the number of neutrons. What other thing does it also indicate? So the mass is the mass just neutrons by itself?
It's both neutrons and protons.
Exactly. Yeah, it's basically the mass of the nucleus. And because the mass of the electron is so damn small, it's about 1/4000th the mass of a proton. Basically, 99.999% of the mass of an electron, of the atom is in the nucleus. And so the atomic mass is equal to the number of protons plus the number of neutrons. So it's both. So the atomic number tells us what element it is, and the atomic mass tells us which isotope of that element it is. So each one of these, so an atomic mass refers to basically a single atom. Because we know that if we look on the periodic table, and we'll be doing that a lot today, when we look at the periodic table, we're given a number like this, like 37.16. Now, if the atomic mass of a proton is 1, and the atomic mass of a neutron is 1, how can we have an atomic mass of 37.16?
It's the average of all the isotopes.
You're really faint, but I think I got you. It's the average, right? That's what you said?
Yeah.
Yeah,
All the natural isotopes.
exactly. It's the average. It represents the average of all the atoms that we can measure. So if we take a mole of aluminum, for instance, most of it is going to be one particular isotope, and then it'll be another one that's slightly heavier or lighter, and maybe a third one that's heavier. For instance, oxygen's atomic mass, average atomic mass, is 15.999. Now, what that means is that basically all of the oxygen has an atomic mass of 16, and there's very, very small number of it that has an atomic mass of 15. So this means 16 is like, 99.9% of it. And then 15 is a very small number. But when we add them together, when we add the total together, we come up to slightly less than 16. So 37.16 would mean that most of the isotopes have a mass of 37, some a little bit more, and maybe some a little bit more than that. But the majority would have a mass of 37. So let's do this first one. So if I have an atomic number of 20, what does that tell me?
The element.
Exactly, it tells me which element it is. And so to find that out, let's look at oops. See if I can get, here we go. So here's my, keep having things pop up. So everyone can see the periodic table now, hopefully?
Yep.
Yeah.
Good. Right, so ptable.com. You should have that bookmarked by now, hopefully. So this gives all sorts of information, pretty much everything you need when you're looking for information about different elements. So for atomic numbers, which number is the atomic number? The one on top or the one on bottom?
It's the one on top, right?
Right, because it's the only number that you'll see that has, that's a single integer. The rest are all going to be averages. They're all going to have numbers past the decimal. They're going to have, tenths and hundreds and thousands. But the atomic number cannot. The atomic number has to be an exact number. 1, 2, 3, 4, 5. So which element has an atomic number of 20?
Calcium?
Yep. So calcium is an atomic number of 20. And you can see from here that the atomic mass, it's generally about twice as much. There's usually about twice as many neutrons as protons. But as you get bigger, as the elements get bigger and bigger and bigger, there's actually more neutrons than protons. But once we get up to around element 30 or so, element 25, 26, we start getting more neutrons than protons. So when we get to the really big elements like uranium and stuff, there's a lot more neutrons. Why a lot of the really big ones are radioactive. Too damn many protons. Too many neutrons. So here we know that our element is calcium. So we can go back and look at our isotopes here. So our isotope name, the first thing in our isotope name. So our isotope name will have first the element name, followed by a dash, and then the atomic mass. Okay, so our isotope name we can pretty much fill in here. So what's our name?
Calcium.
Calcium. Yep. So that would be calcium. And yeah, you can see that my handwriting is not really, it's tough to write on the screen. So calcium. So what is our symbol for calcium?
Ca.
Ca, right? Small a, right?
Mm-hmm.
And you can see from tantalum down here, this is how we draw, this is how we make the symbol for the isotope. We have the atomic mass above and the atomic number below. So how are we going to do this for calcium 37? Where does the 37 go? Where does the 20 go?
20 on the bottom, 37 on top.
Yeah. 37 up here and 20 down there. And so for the isotope name, we would just have calcium dash 37. Okay. So how many protons does that give us?
20.
20. Yeah, that's always going to be the same number. The atomic number is always going to be the number of protons. So we can, so that one's easy. This one's a little trickier. How many electrons?
20.
Why 20? Why couldn't it be
Because it doesn't
19
have
or
the
21?
plus or minus.
Exactly. It's not given a charge. So if it's not, if we don't see a plus sign or a minus sign, we immediately have to assume that it's a neutral atom. And if it's a neutral atom, the number of electrons and protons have to be identical. So yeah, 20. Then how many neutrons is it going to have?
17.
Mm-hmm. Yep. So the atomic number plus the number of neutrons will equal the mass. So this is P and this is N. This is P plus N is the mass. Okay, so second one's a little trickier because it only gives us electrons and neutrons. We don't know what the number of protons or therefore the atomic number is. How are we going to figure that out if we don't know what the number of protons is? Because that could easily be calcium, because calcium normally has a charge of +2. So that just could be calcium again. How are we going to figure that out?
I have a question. For the protons and electrons, are they always the same, or was it just a coincidence for calcium?
They will be the same if there's no charge.
Okay.
That's not always going to be the case.
Okay.
So here, the second example, we've got 18 electrons, but we don't know how many protons we have.
Okay.
How are we going to figure that out?
Well, since it says neutral isotope, that means it's also 18.
Somebody read the question. Exactly. Yeah, these are all going to be neutral. So none of them are going to have a charge. Excellent. Yeah, that's what neutral means. And without that, there'd be no way of determining how many protons there are, because it could be 20 again. Because like I said, calcium, usually when we find it, calcium in solution, if it's an ion, is always calcium 2 plus. So that could very easily be calcium 2 plus. That would make a lot of sense. But since it's a neutral isotope, it's not calcium. So what element is that then? So that gives us electrons will be the same as the number of protons. So what element has an atomic number of 18?
Argon.
Aragon.
Argon. Let's have a look. Hopefully everyone's got their
What's
18.
for the
Argon, that's right. And there's no way that argon is not going to be neutral. As we'll learn, the noble gases do not form ions, like ever. So they are not going to be charged. So you're always going to see the same number of protons and neutrons with neutral gases. Right, so that is going to be argon. So argon, whoops, draw again. So argon. And which isotope are we dealing with?
Neutral? Argon 38.
Argon dash, what will we put in? Remember, we put in the mass here.
38, right? 18 plus 20.
38, right, because we've got 18 protons and we've got 20 neutrons for a total of 38. So we would write in argon 38. So what's our symbol? What's our isotope symbol for argon?
38 over 18 AR.
38 on top, 18 on bottom, and R. Yes, that's right. Argon is R. And a lot of times when you see in the isotopes, sometimes the atomic number won't be there. Sometimes you'll just see 38 argon. And the reason for that is if we know what the element is, we already know what the atomic number is. We already know it's 18. And so it's extraneous information. But the reason why we usually put it there is because it gives us an opportunity to immediately determine how many neutrons. Because since that's what separates the isotopes, we would like a quick way of figuring out how many neutrons there are. And so if the atomic, because you can't memorize all the atomic numbers, at least most people can't. I can't certainly. And you want to know how many neutrons there are because that's the difference in isotopes. This gives you an easy way of figuring it out. So you just subtract the top number from the bottom number and you automatically get it. Okay. So we'll do one more and you guys can do tantalum by yourselves. So cobalt 64. That's it. That's the only information we get. So there's one thing we can automatically fill in immediately. Is it the atomic number, the mass, protons, electrons, neutrons? What number do we immediately know just by looking at that?
The math.
Cobalt 64. The mass. Yeah, we immediately know, well, okay, that's 64. Whoops. Gotta be. So that's 64. But it's cobalt. So, the other thing we can do, cobalt, and put a 64 up there. That's the other thing we can figure out. That should be an O, not an A. Man. Yeah, 64, cobalt. So, but we don't know, or I don't know at least, maybe some of you geniuses have memorized it already. I don't know what the atomic number of cobalt is, so I'm going to have to look it up.
27.
So let's see. Cobalt is a transition metal. Someone's already found it. Good for you. 27. Yep. 27. And one of the bits of information that you get from the periodic table here, and we'll be getting into the chapter after this one, it gives you the electron configuration, which tells you how the electrons are arranged around the nucleus. So it shows you for cobalt, in the first shell, there's 2. In the second shell, there's 8. In the third shell, there's 15. And in the fourth shell, there's 2. So that will be really, really important for determining its chemical characteristics, is how many electrons are there in the outermost shell. Because we haven't got to this yet, but we call those valence electrons. Valence electrons are the electrons in the outermost shell furthest away from the nucleus that are involved in forming bonds. And so for cobalt, there's 2 in the outermost shell. So it usually has a charge of +2 because it gives those away. But we'll find out, since it's a transition metal, it's sneaky, and it doesn't always do that. So our atomic number is 27. So let's go back to 27. Come on. It won't show me. Where is the hell? Let me go back. Okay, here we go. So 27. So we know the atomic number is 27. So let's put that in here. Now, what about the rest? So how many protons is that?
27.
27. That's not a tough one. And we could also put our 27 in the isotope symbol because the mass is on the top and the number is on the bottom. So we can also put our 27 here. 27. So how many electrons?
27.
27. It's neutral. It's an atom. The minute you say atom, it means it doesn't have a charge. Because if it does have a charge, what do we call it?
Ion.
Ion. It immediately becomes an ion. If you change the number of electrons, it's immediately an ion, either a positive ion or a negative ion. But if it's an atom, atom means neutral charge, same number. So how many neutrons, speaking of neutral, how many neutrons do we have? I have to do some math for this one.
37.
37, very good. Yeah, so you can see the bigger and bigger the elements get, the number of protons always goes up by 1, but you can see as we get bigger, the number of neutrons increases even more. So when you get out to like I said, uranium, I think its number is like 92 or something like that, and its atomic number can be like the mass could be like 235, 238. It gets really, really big. And so the last one down here, you guys are going to do for yourselves, but Ta is tantalum, which is it's an exciting metal, tantalum. And there's the number, there's its atomic number, and there's its atomic mass. So hopefully you can figure those out on your own.
I have a question. How do we figure out how many neutrons is there again? What's the equation for that?
I'm sorry, the car went by. I didn't quite hear you.
How do we figure out the number of neutrons again?
Oh, the number of neutrons. Now, the number of neutrons and the number of protons together give you the mass.
Okay.
Because like I said, electrons are super duper tiny. So you could have 1 billion of them and it doesn't really increase the mass very much. So all the mass is in the nucleus. So if you know the number of protons from the atomic number, the number of protons plus neutrons is all the mass you're going to have. So basically, you just take the mass, subtract the number of protons, and that gives you the number of neutrons.
Thank you.
Yep. Okay. All right. So which one would you like to do next? Oops, the hell is that? Where is my, oh great, now it's just gonna, all right, I am going to start this again. How do I, oh, wait a minute. Oh, there we go. There we go. That's what I was looking for. So which question would you guys like to do next? We can do any one of them. So we finished this. Which one do you want to do next? 2. Basically, question 2 is all changing units. Hopefully, so we can do 1 or 2 of those if you'd like. And then number 3 is formulas, which we haven't really got to yet. So we'll definitely spend some time on that, because that naming compounds is part of chapter 2. Formulas and names. And then on the bottom, this one, we could actually do this one right now, because now we're introducing ions. So we need, so for each one of these isotopes, we need to figure out the number of protons, neutrons, and electrons, because we have a charge. And then, well, 6 doesn't show up for some reason. And then 7 is how you calculate average atomic mass. And we can definitely go through that as well. So anyone want to do first in particular?
Can we do either 2A or 2B?
Sorry?
Can we either do 2A or 2B, please?
Oh, sure. Okay. Yeah. So yeah, A is a little bit tricky because we're dealing with measurements we haven't really seen before. We've got microliters and we've got decimeters cubed. Like, what the hell, decimeters cubed? So first thing we need to do is figure out how are we going to relate these two? Like, basically, what is a decimeter? Anyone tell me how long a decimeter is? Deci. It's one of those, we sort of skipped over it this morning. How long is a deci, in meters, how long is a decimeter?
A tenth.
A tenth, really good, yeah. So it's 1 decimeter equals 0.1 meters. Now, microliters. How big is a microliter? In terms of liters. So if I have 1 microliter, how many liters is that?
10 to the negative 6.
10 to the negative 6, yep. Now, something else we can, what have we learned so far about how big is a liter and how big is a milliliter? Anyone remember the size of a liter in terms of cubic centimeters? So 1 liter is equal to a certain number of cubic centimeters. Do you remember how many cubic centimeters that was?
1,000.
1,000, that's right. So 1 liter is equal to 1,000 cubic centimeters, which also means 1 milliliter is equal to 1 cubic centimeter. And an easy way to remember this is that 1 mil of water weighs 1 gram. And so that's how it's related. A liter is equal to a kilogram, is equal to 1,000 cubic centimeters, because 1 gram of water equals 1 mil, or 1,000 grams equals 1 liter. That's how I keep it in my head anyway. So we've got to figure out some way. We use all this information over here to get us from decimeters to liters. We need to figure out some way we can move that from one to the other. So what's another way of expressing a decimeter? If we were to convert that to centimeters, how many would it be?
0.1 centimeters.
Mm-mm. Now, 1 decimeter is 0.1 meters, or 100th of a meter.
10.
Or I'm sorry, 1/10 of a meter. So 1/10 of a meter, how many centimeters is that?
10.
10, that's right. Because deci means 1/10, and centi means 1/100. And milli is 1/1000. So there must be 10 centimeters. 10 divided by 100 is equal to 1/10. So there must be 10 centimeters in 1 decimeter. So 1 decimeter cubed is also equal to 10 centimeters cubed. Now, this is the mistake that most students make. They don't cube both. You have to cube both the unit and you have to cube the value in front of it when you're doing this sort of thing. So 1 decimeter cubed, we're basically cubing both those things. The 1 stays a 1 because 1 times 1 times 1 is 1. But when we're cubing the 10, now you can see that 1 decimeter cubed is equal to 1,000 centimeters cubed, or 10 times 10 times 10. So at least we figured out this side. This side gives us 1,000 cubic centimeters. And 1,000 cubic centimeters should look familiar. What volume? Remember, this is cubed, so this is a volume now.
That's a liter.
That's a liter, exactly. 1 decimeter cubed is equal to 1 liter. So what we've basically done is we've looked, this is what our conversion is. We want 2.33 times 10 to the 5th microliters, and we basically want to convert that to liters. That's what this really boils down to. So let's do that. Let's write out how we would actually do the whole thing. Oops. All right. So here's what I've got. I have 2.33 times 10 to the 5th microliters. Now, what am I going to multiply that by to get to liters? What unit do I put on top? What unit do I put on the bottom? I want to end up with liters. So where do I put liters? In the numerator or in the denominator?
Numerator.
Put it in the numerator. I always put what I want on top because that's what's going to be left. And what I want to get rid of, the unit I want to get rid of, I'm going to put that on the bottom. Now remember, as I said this morning, every time we multiply a number and a unit by something to change the units, it has to equal 1. So the number of liters I have here has to equal the number of microliters here. It has to be the same. They have to equal 1. So what am I going to put for liters and microliters? What's the
Liters will have
relationship
1.
between them? Excuse me?
The liters will be 1 and the microliter will be 10 to the power 6.
There you go. You could also do it the other way around. You could also have 1 microliter is equal to 10 to the minus 6 liters. That's the same thing. They're both, either one is the same because they both equal 1. So as long as that relationship equals 1, as long as those two things are equal to each other, it doesn't really matter if you put the big number on top or the big number on the bottom. Either way is fine. Oops, undo. There we go. All right, so now we have the unit we want to change. We have a factor that will do the changing of the units for us. So we can basically just, oops, I can basically just subtract, I can eliminate microliters. I'm left with liters. So how many liters is that?
0.233.
Right. So since we're dividing 10 to the fifth by 10 to the sixth, we just subtract them, right? So we would get 2.33 times 10 to the minus 1 liters. And we could change, since it's 10 to the minus 1, we could also just 0.233 liters. And since the unit we actually want is decimeters cubed, instead of liters, we could just substitute decimeters cubed. We could also do that up here. We could add another one saying 1 decimeter cubed is equal to 1 liter. So get rid of our liters and be left with decimeters cubed. Either way. But in order to do it, you have to see what the relationship is between volume and length. And so our volume is liters and the length is decimeters. So we have to figure out some way to convert a cubic length to a volume. So that's the first thing. That's the first thing we did here. So hopefully that's clear. I maybe explained it the wrong way around. But it's important you recognize that 1 decimeter cubed is the same as 1,000 centimeters cubed, which is the same as a liter. Without that information, you'll never be able to get it. Okay. Any questions about that particular one?
There's a question in the chat
Okay.
that says if 1 cubic decimeters equals 1 million micrometers, can you just directly divide it?
Yeah. Yeah, that works too. Yeah, if you just show me how you did that, yeah, you could also show that 1,000 cubic centimeters is the same as 1 million cubic millimeters. And a cubic millimeter is a microliter. Yeah, you could do it that way. I sort of like finding the one sort of unit I can relate one to the other by. And generally I find cubic centimeters being a milliliter is the easiest way to do it, but there's a lot of different ways you can do it. Yeah, as long as you, whatever unit you have equals the number on the bottom, you can do it any way you like.
Can you just memorize that decimeter cubed is the same as a liter? Because that's kind of common conversion.
Mostly, no, I just remember 1,000 cubic centimeter. A cubic centimeter is a milliliter. That's like, that's stuck in my brain. So
not have to do that every time.
no, if you can remember that a decimeter cubed is a liter, you're off to the races. Just do that. Yeah, I just can't remember that all the time. This is the number that's stuck in my head. 1,000 cubic centimeters is a liter. But yeah, if you can remember that a cubic decimeter is a liter, just do that.
All right, thank you.
Yeah, there's no one way of doing these, especially when you're changing units, like metric units back and forth, because there's all kinds of different metric units. You know, there's one for tenths and hundredths and thousands and millions, and so yeah, you can basically, and you can use any combination of them you want as long as you get to where you need to go at the end. Everyone should have, no matter what you do, you should have the same answer at the end of it. Okay, so what's the next one you want to work on? You wanted to do 2 as the second one as well? you also want to do the second one? Why don't we just do that one together? Because I'm gonna need some help for that one, because I don't remember the conversion of ounces. So someone's going to have to look that up. So let's just get started on it, and someone can help us. So anytime I have a question like this, I always write down what numbers do I have, what numbers do I want to get to. So what I have is 4598 ounces. Now, in this particular instance, ounces is a unit of mass, although ounces is also a unit of volume. So this is a tricky question, but when you see ounces like that, well, I guess we don't really know which one it is. That's one of the confusing things about this stupid imperial system. How can you have ounces as a mass and as a volume? That doesn't help. So let's just assume it's let's just assume it's mass, because if it wasn't mass, if it was a volume, we wouldn't need the density, right? We could just convert volume to volume and we'd be done. But since we have the density here, I think that means that we're going to have to treat this as a mass. So what's the conversion we're going to need?
So 1 ounce is a 28.35 gram.
There you go. Yeah, we need to convert mass to metric mass. So we need to multiply this by something. So what are we going to multiply it by? We want grams, and we want to get rid of ounces. So our ounces will cancel and be left with grams. So what was the relationship again?
1 gram is a 28.35. 1 ounce is 28.35 gram.
28.85?
35.
35, that's what I thought. Yeah, that sounded, 85 sounded wrong. Okay, so that gets rid of our ounces and we're left with grams. But we don't want grams, we want mils. So I need to multiply it again by something that will give us mils. So what am I going to put on the top and what am I going to put on the bottom?
Mils in the top and grams in the bottom?
Yep, I want mils. So that's the unit I want. I always put that in the numerator. And the unit I want to cancel, which is grams, I'm going to put that in the denominator. So what do I put here? So this is my conversion of mass to mass. And this is a conversion of mass to volume. So what numbers do I put in here? This I can just look up from any table. But this is different. This is a mass to volume. And when we're dealing with mass and volume, what are we dealing with?
Density.
Exactly. We're dealing with density, because that is the thing that relates mass to volume. So what am I going to put as far as milligrams or grams and milliliters here?
I think 1 for milliliters and 19.32 for grams.
Right, because that is the density of gold. And that's what we're looking for. We're looking for a volume of gold. We have a mass of gold, and we want to convert that to volume. So this number is going to be very specific for gold only. This number is going to be general for anything, because it's just mass converting one form of mass to another form of mass. And so it doesn't really matter what the substance is. If it has mass, I can just express it in either ounces or grams. But the density is very specific, as we learned in our lab. It's an intrinsic property. It's different for every element and every compound. So we have to make sure we have it for gold. So 1 mil is equal to 19.32 grams. So I can cancel my grams and I'm left with mils. So that is correct. So what is my answer? If you're going to make me do the math too, man, you've got another thing coming.
67.47 milliliters.
Let me double check. So your answer is 67.47 mils. So why so many digits?
Because the least amount you have is 4. Do you include the 1? Do you just ignore that 1, or
Which one?
like the
This?
one on the bottom, the 1 milliliters? Yeah, do those count?
No, because those aren't measurements. That's a count. If we're counting, that means the exact number. So it's not 1.0 mils. That's a measurement. 1 mil, when we're counting the number of mils, that's an exact number. So that's also equal to 1.00000 indefinitely. Whenever you're counting something, it's an exact number. So like there's not 12.0000000 eggs in a dozen. I just say there's 12. But because it's a count, it's an exact number. Yeah, that's a really good point, because that we're not measuring an ounce, we're defining an ounce. And so that has an infinite number of significant digits. Yeah, that's a good point. But you were right. 4 is the number of significant digits, because there's 4 significant digits in my mass of gold, and there's also 4 significant digits in my density. And so since my multiplying and dividing all have 4 digits in it, my answer should have 4 digits as well. Yeah, so 67.47 milliliters, which is a nice hunk of gold, actually. What's gold going for these days? Like $1,000 an ounce or something? Probably more than that. It's been a while since I've checked the price. Okay. So C you can probably do on your own. D is just another volume change from cubic lengths. So just make sure you get the lengths right. And then actually E, why don't we just do a quick rundown on aluminum nitrate, because we haven't really got to compounds yet. And so you're not going to know how they go together. So aluminum nitrate, what's the symbol, chemical symbol for aluminum?
AL.
Al, right. That's Al. And you're not going to know what nitrate is, but I will let you know that it's NO3. Nitrate is what we call a polyatomic ion. It's not a single atom. It's a number of atoms that are bound together that together have a charge. So the whole thing, we treat this as one unit. That is one unit, and it has a charge of -1.
Are we going to
Nitrate.
get to memorize the polyatomic ions, or at least the common ones?
Well, I mean, you're going to be able to look them up. So I've memorized some of them, but not all of them. But you'll be able to look these up. And if it was on a test, like if we were all together, I'd just give you a sheet of the common ones. No, because I don't like people memorizing things. Memorization is not understanding. So I'd rather you spend your time learning how to do it properly than memorizing these silly things. But nitrate is -1. Now, let's go back to P table. And oops.
So it's going to be 2698
Yeah. So the other thing I want
for aluminum.
to point out is which group is aluminum in. Now the group number will be on the top.
5. Actually, it's 3.
3. It's in group 3. And most of the metals, we'll find out that the metals in group 1 have a charge of +1. The metals in group 2 have a charge of +2. Aluminum's in group 3. What do you think its charge might be?
3.
Yeah. So this is and we'll learn this next week as well. This is an ionic compound. An ionic compound consists of a metal and a non-metal. So aluminum is our metal, and our non-metal is this polyatomic ion. So that is a non-metal. When you have the two of them together, they form an ionic compound, because aluminum will have a charge, and its charge is +3. And the nitrate ion has a charge of -1. So when I write aluminum nitrate as a compound, how am I going to write it, do you think?
Aluminum nitrate.
So how many atoms of aluminum and how many molecules of nitrate are going to go together to form this compound?
Aluminum parenthesis nitrate 3.
So you're saying aluminum and then parentheses nitrate and then another 3 here?
Mm-hmm.
That is correct. Very good. Yeah, because we'll learn that the charges have to balance. Just like atoms, compounds have to have no charge. So atoms don't have a charge, ions do, and compounds don't have a charge, ions do. So the charges of the ions in a compound have to balance. And so if we have +3 here, we got to have -3 here, so that the whole thing balances out. And so it takes 3 moles of nitrate to go with 1 mole of aluminum and give us a balanced compound. So this, someone look up aluminum nitrate and tell us that that is the right structure for it. That's the right formula.
Yes, it is.
Excellent. So yeah, good job, whoever it was that gave me that. So another thing you can do while you've looked it up, you can look up the mass. Now there's 2 ways you can do the mass. You can do it the hard way or you can do it the easy way. I kind of like doing it the easy way.
So the easy way is going to be, I think, 212 and 996.
The easy way Google tells you.
Yep.
Yeah, so Google tells us what's the number?
The molar mass for the aluminum nitrate will be 212.996 gram per mole.
Yeah. Okay. Now, if you wanted to do it the hard way, you could look up the mass of one, just from P table, you could just look up the mass of 1 atom of aluminum. How many atoms of nitrogen do we have?
3.
3. So we have 1 aluminum, 3 nitrogen. How many oxygens?
9.
9. That's right. Man, you've taken chemistry before. Yeah, so there's 3 atoms of nitrogen in every molecule of nitrate, and we have 3 molecules of nitrate. So we multiply 3 by 3, and we have 9.
Is it easier to calculate nitrate ion this time and remember it next time?
If you want to memorize the atomic mass or the molecular mass of nitrate, please feel free to do it. I don't know if anyone who does that, but yeah, I mean, what I would do is, like, I mean, if I have a computer in front of me, I'm just going to Google, molecular mass of aluminum nitrate. Boom. There it is.
Because previously, when I was in high school chemistry, the molecular mass and the molar mass were rounded to the nearest gram, so that was
use the most accurate. No. Use the most accurate mass you can find.
Okay.
Don't limit. I'm going to say this over and over and over. Do not round anything until you get to the final answer, because if you start rounding numbers before you get to the end, basically you're introducing imprecision into your answer. And so you're making it artificially less precise than it needs to be. So don't do that.
Yeah.
Like for instance, if you've taken all the time to calculate the mass of, you found the mass of aluminum, you found the mass of nitrogen, you found the mass of oxygen, and then you work it all out. There'd be no reason to get to 212.996 and then round it to 213. No, use the whole thing.
Yeah,
And then
I know that was
round at the end.
because for calculation, yeah.
So even I think, I don't know, I can't remember, on P table, I think they give you at least 3 digits past the decimal and sometimes more. So use all of them. Don't round till you get to the end. Just if your calculator carries 15 digits, use all of them for your calculations. And then when you get to the very end, determine how accurate you need to make that answer based on the information.
A lot of differences in the take place in high school and college chemistry.
I would hope so. Yeah, hopefully you're learning a little bit more than you did before. I mean, we're not saying that the high school chemistry is wrong or anything, but if you're particularly, since this is a lab course, you really have to understand where error comes from. What are the sources of error? And this is a classic source of error, is taking measurements and rounding them too soon. So don't ever round measurements until you get to the absolute end of the problem, and then determine how accurate does my answer need to be. Because if you do that, like I said, you are introducing error into your answer that you don't want. So if you look up on Google, like what's the atomic mass, what's the molecular mass of aluminum nitrate, and it gives you 17 digits, use 17 digits. And hopefully your answer and someone who uses only 6 digits should be the same, but it might not. But use as many as you can find. So with this number, whoops, I need to do a conversion. I need to convert I need to convert grams to moles. So I have, whoops, here we go. I have 250 grams, and I want to convert that to moles. So how many, where am I going to put moles and where am I going to put grams in my conversion?
Moles per gram.
So moles on top, right?
Mm-hmm.
And then grams on the bottom. So here's where I would plug in my 212.996 moles. So how many moles is that?
1. Oh, sorry, never mind.
No, this is 1. Yeah, 1 mole is indeed equal to 212.996.
Okay.
1.173.
1.173. Keep going.
70.
70. Okay.
Actually, there is a 3 instead of 0.
3 after or before?
Before.
Before. So 7373.
Yes.
Okay. Now we forgot about something. Where does my 85% pure enter into this? Now, if I have a compound that's only 85% aluminum nitrate, what do I do with that information?
Multiply that by 85%.
Multiply what by 85%?
1.17373 grams.
Right.
by
I could do it.
85.
Yes, I could do it at the end, or I could have done that with the mass. I could have taken my 250, which we probably should have, multiplied that by 85%. So if I multiply by 85%, what's the number I multiply by?
0.85.
Yeah, either 0.85 or 85 over 100. Either one. It's the same thing. So basically what happens is I need to multiply this by 0.85. So what's my final answer?
That is 0.97.
0.997.
How many significant digits can I report?
3.
Three.
Use
3?
99. Yeah.
3.
Nope.
4.
2.
Nope. 2. Who
6.
said 2? Yes, it's 2. 85 only has 2 significant digits in it.
Oh,
Yeah. I deliberately changed this question because I want it to be mean. Yeah, there's 3 significant digits here. 250 with a decimal point. That's 3. But 85 only has 2. So I can only give 2 significant digits. So what am I going to do with this number and give 2 significant digits?
Round it.
I have to round it. 1.0.
1.0.
Excellent. Yes. Because this will round to 1. I need to get rid of this one. So this 99 rounds to 100, but I could only give 2 significant digits. So I get rid of that, and my answer is 1.0 moles. Yes, Nicholas.
I'm not sure if I have the same paper, but mine says 85.0%. Would that make mine
Oh,
3
does it?
sig figs?
Oh, yes, yours would have 3. So
Okay.
yours would be 997 or 998, depending if you have to round the 7.
Okay.
Oh, man, so I made some of them 85.0? Damn. I want it to be trickier than that. Yeah, whatever number you have on yours. Yeah, maybe I've got maybe I put a typo on my own.
The file on Canvas had 250.0 and 85.0.
Damn it. All right, you got to round my trickiness then. All right, yeah. So for the rest of you, for me, my answer will be 1.0. For you, your answer will be 0.997 or 998, depending on what the next digit is. But you can see what a big difference that makes. I mean, that makes a big difference. So you have to look real carefully. Yeah, thanks for pointing that out, because yeah, mine is not 85.0. Good work. Okay. So number 3, I'm just going to just show you a couple of them because we're going to be doing this.
A question
on
in
Tuesday. Yes, question.
the chat.
Okay.
A question regarding six figs. If we have a problem that is like multi-step, do we convert to six figs that at the very end, or do we do
Only
each
at the
part?
very end. Only the very end. So if you had to convert like 4 things, use as many significant digits in your conversion as you can find. So whatever part of this particular question gives you the fewest number of significant digits, that's the number you find. So for instance, if you could only find a molar mass in grams, that would still give you 3. If one of your conversions between, like, let's say ounces and grams or something like that was only 2 significant digits, I mean, it shouldn't be. You should be able to find at least 4 or 5. Whatever, when you're doing your conversions, whichever one of those, the conversion shouldn't interfere with the number. You should have at least 4 or 5 significant digits in every single one of those. The limits, the
Excuse me.
limitations on the significant figures should come from the question.
Excuse me.
Yeah.
So, if 85%, I mean, if 85%, I mean, is 6 fix, but when it comes to 8%, you would only get one 6 fix.
Yeah, you'd only get 1. If it was 8% without like 8.0, that's only 1. Yep.
So
you'd have a very inaccurate answer there.
Okay.
Which is why you probably wouldn't see 8%. You'd see at least 8.0.
Okay.
Yeah, because if it's just a single digit, that's not a very accurate answer. But you're right, 8% would only give you 1 significant digit, which isn't a lot. All right, so formulas. A formula, we'll learn that a chemical formula is just basically the element, not the names, but the symbols put together in the right number. So sodium.
You know how is the assistance could be text, yeah?
What's that?
Like, oh, never mind.
Oh, okay. You're talking to somebody else. So when we have these, when we have a name like this, so these are names. So these would be the names, and then we're looking for the formulas, with just the chemical symbols. So any name, the beginning of it usually gives us the more positive. If it's an ionic compound, and remember, an ionic compound is a metal plus a non-metal. And metals are almost always charged, unless they're just by themselves or bound to another metal. They're pretty much always charged. And the non-metal, and usually with a plus charge, almost always with a plus charge. And the non-metals are almost always with a minus charge. So those are the ionic compounds. Now, a covalent compound is not ionic. The electrons are shared rather than stolen. And so nobody has a charge. And those are generally between 2 nonmetals. So when we look at the periodic table, see if I can get to the... So we look at the periodic table, we'll see, you remember where the metals were and where the nonmetals were?
Yeah.
So the nonmetals are all on the right side. They're all on this side, or I don't know, kind of hard for me to know how it's going. Oh, it's on your right. So the nonmetals are on your right. And
except hydrogen.
Well, hydrogen can be both. Hydrogen is one of those weird things that can be both metallic and non-metallic. It's pretty much one of the only ones that can do that. And there's usually a ladder. For some reason, they don't have the ladder here, but the ladder goes like this.
Yeah. Excuse me.
Yeah.
Why this helium goes this left side? Usually helium goes right side.
Oh, it's just a different way of putting them. Yeah, usually helium is here.
Right now you're showing the electron configuration table. I think it would be better to properties, maybe.
Yeah, if we changed it to isotopes or properties, it would move.
Okay.
Yeah, see, it pops right back over. I just wanted to do it on electrons because it's got the colors here, which are a little bit different. And so all the nonmetals are over here on the right side. So it's these. All the elements that are right along the ladder here, those are called the metalloids, like silicon and arsenic, tellurium and antimony. Those have both metallic and non-metallic properties. We'll talk a little bit about them, but not very much. Although, silicon is kind of important in this particular valley, as we would say. So we'll talk a little bit about that. So these are the So these are the non-metals here. And since the furthest right are noble gases, it's really only these. There's very few non-metals. You can count them on like 2 hands. So they take electrons generally from metals. And so that's how you form ionic compounds. Everything else in the periodic table is a metal. So you can see that it's vastly metals. Everything on the left side, everything in the middle, everything on the bottom, those are all metals. So metals give electrons away and become positively charged. Non-metals take electrons away and become negatively charged. So we go back to the formula, we have a look. So sodium sulfide. Is sodium a metal or a non-metal?
Metal.
Sodium's a metal. And what about sulfide?
Bigger.
Excuse me?
Could you make the PPT bigger?
Make what bigger?
The PowerPoint?
I don't think I can make it any bigger than it is right now. You should see, this isn't the whole page filled?
Okay.
Is it?
No.
No, it's a really small portion.
Oh, it's really
It's
small. Oh, okay.
small.
Okay. That's for me, it's really big. How about that?
There's like a whole black outline.
Oh, okay. I got you. Is that better? Or
Yeah.
is that same size?
Yeah, it's the same size.
Maybe.
Did that change it at all?
Mm-mm.
Let me try something else.
Maybe the posture.
Okay. Oh, I got you. I got it. I think. How about that?
Yeah, that one.
Yeah.
I was sharing the wrong thing. It has both the slideshow and the PowerPoint file. So if you don't share the slideshow, it's really, really small. Okay, good. Yeah, so sodium is indeed a metal. Now, sulfide. What does sulfide mean? What's the "ide" part?
Ide means one atom, not one atom, not grouped ion.
Not
Anion.
ion. I don't know what a not grouped ion means.
Like without oxygen. And anion, A-N-I-O-N.
Oh, anion. That's what you're saying. Yes, anion. It's a negatively charged ion. If it's an ionic compound, we've already figured out it's an ionic compound because sodium is a metal. So because sodium is a metal, automatically this is an ionic compound. So we put down sodium. Now the "ide" part.
S2 negative.
We put "ide" at the end because basically it's the second part of the compound. So we use "ide" as a negatively charged ion if it's ionic, but we also use "ide" if it's just if it's a covalent compound like carbon monoxide or dioxide. It just means it's the second thing. That's really all the "ide" means. It's the second part. But since this is an ionic compound, that means sodium is going to be positively charged. And the sulfide or sulfur is going to be negatively charged. So in order to figure out what the charge is, we need to go back to the periodic table. Oops, excuse me, back to the table. So
We
we're
need
going to go back to the table. So here, we're going to learn a little bit before class how we can figure out what these charges are going to be. And the way we do that is by finding out what group they're in. So what group do we find sodium in?
chalcogen, calco, CHALCOGEN.
Now, what's the group number? I'm asking for the group number.
One.
Okay.
1. Yeah, it's in group 1. So it's right at the top here. So group 1. So this is a metal in group 1. We call those the alkali metals. And they're in group 1. We'll also notice that since we're dealing with electrons, let's just click on it. We notice that it has 1 electron in its outermost shell. 1. And what we're going to learn is that in order to achieve stability, you want to have 8 electrons in your outermost shell. And so the way for sodium to get 8 electrons in its outermost shell is to get rid of that 1. Oops. And so it gives it away. It gives away that electron and becomes positively charged. And if it gives away 1 electron, what's its charge?
10.
+1.
+1, exactly. Now it has 1 more proton than electron, and so its charge is +1. +1. And that's why we put these things in groups. We'll learn why the periodic table is called the periodic table, is because these chemical compounds, the way that they arrange themselves, the chemical characteristics are periodic. And so everybody in the first group loses an electron. Lithium, sodium, potassium, rubidium, cesium, francium, they all lose 1 electron because they all have 1 electron in the outermost shell. Look at potassium has 1, rubidium has 1, cesium has 1, francium has 1. So they all have 1 electron in the outermost shell, and they all lose that 1 to achieve stability, and they all have a charge of +1. But sulfur is a little different. Let's go over and find sulfur. Sulfur is way over there. What group is sulfur in?
8.
Non-metal.
It's a nonmetal. What's the number of the group it's in?
16.
16. We can actually call, we can just call it 6 though. The shorthand for these are 3, 4, 5, 6, 7, 8. But
Okay.
16 just because we have all the transition metals in the middle, and we'll talk about the transition metals in a while. But let's have a look. How many electrons does sulfur have in its outermost shell?
6.
6. Now remember, I said the magic number is 8. Every atom, with the exception of hydrogen and helium and lithium and beryllium, but most all the other atoms want to get to 8. They want to have 8 electrons in their outermost shell because that's what argon looks like. If I click on argon, argon has 8 electrons in its outermost shell, and it's mellow as hell. It's totally chill. It's because it has achieved the chemical nirvana of having all of its electrons filled. All of its electron shells are filled. And every atom wants to get there to achieve stability. Sulfur's only got 6 electrons in its outermost shell. So the way for it to achieve chemical stability is either to lose 6 electrons or gain 2 electrons. Which one do you think is easier to do?
Gain 2 electrons.
Yes, it gains 2. So it basically steals 2 electrons from whoever else it can steal them from. In this case, it's going to be sodium, because metals like to give away electrons. They have fewer electrons in their outermost shell, so they're easier to get rid of. Sulfur needs only to steal 2 more electrons and it achieves stability. So when sulfur steals 2 electrons, It now has 2 more electrons than protons. So what's going to be the charge on sulfur?
-2.
-2. That's right. So sulfur is going to have a -2 charge. And we'll find out that oxygen does exactly the same thing. Oxygen has 6 electrons in its outermost shell and has a charge of -2. And selenium has 6 electrons in its outermost shell and has a charge of -2. And tellurium has 6 electrons in its outermost shell and has a charge of -2. So you can see how this works. Since they're all in the same group, they all have the same chemical characteristics. They all have the same number of electrons in the outermost shell. They all want to get to the same place. They all have the same charge. So when we go back and look at so sodium, we've already written down.
Excuse me?
Oh, yes.
Could you go back to the P table?
Oh, sure. Yep. Okay.
I think there's something called peroxide. Right?
What's it called?
Peroxide. Peroxide.
Peroxide.
Peroxide.
Mm-hmm.
Where the oxygen gets -1.
Mm-hmm.
I'm not sure.
It's not a charged compound. Let's go back. I'll explain. But yeah, we're dealing when they're charged. There's a -2.
Okay.
Let me go back.
Okay.
Here we go. Yeah. So yes, a peroxide is a special compound where you have an oxygen-oxygen bond. This is what hydrogen peroxide looks like. So an oxygen-oxygen bond is fairly unstable because oxygen loves to steal electrons away from other atoms. It's one of its favorite things to do. That's why we call it oxidation, because oxygen's so damn good at it. And so a lot of times what will happen is that this bond will break. And what you'll be left with is each oxygen gets 1 of the atoms in that bond because they both are pulling on it so hard, and that now they'll form what's called a radical. We just put that as a dot. And radicals, a radical is just a molecule with an odd number of electrons. And radicals are extremely reactive. And that's why when you pour hydrogen peroxide on a cut or something, it foams up, because it's that radical that's combining with all the organic material, which is generally, hopefully, bacteria or whatever it is in there, and it's destroying them because radicals are extremely reactive.
What's the difference between that and hydroxide?
Hydroxide ion has an even number of electrons.
Okay.
And so it has a charge.
Okay.
Peroxide, this has an odd number of electrons and isn't charged.
Okay.
That's the difference. Yeah. All right. So, yeah, we're going to get into that. When we get into oxidation numbers, we'll talk a lot about peroxides and that sort of thing. But yeah, I'm glad you're so interested. Gives me a chance to think a little bit. So sodium. Sodium is Na+. And sulfide, as we've learned, -2. So how am I going to write the formula for sodium sulfide?
Move the 2 to the end of sodium.
To the end. So we put the 2 here.
Yeah.
And this is 1, so we put the 1 there. Yeah, to basically do crisscross in order to balance the charges. So I need 2 sodium atoms. And when you have the number of atoms goes at the bottom. The subscript tells you how many atoms. If it's a superscript, it normally tells you a charge. So we have sodium sulfide. So we just need one. So this would be the formula for sodium sulfide, Na2S. All right, let me do this one. Lead 2 oxide.
Lead 2 oxide. Oh, I see it.
So lead 2 oxide. Now, why? What does this mean? Do you think?
The charge.
This 2.
The charge.
The charge of what?
The charge of lead.
That's right. And the reason for that, the reason why don't we have the charge here for sodium? How come we don't have sodium 1? How come we don't put a 1 there for sodium?
Because that's not transition metal.
Man, you should be teaching this class. That is absolutely right. Yeah, let me go back to the periodic table. So the periodic table, group 1 and group 2 metals, the ones way off to the left, are always +1 and +2. Always, always, always. They're never anything else. Sodium is never anything but +1, ever. And same with magnesium and calcium and strontium. They're always +2. They're never anything else when they form ions. But the ones in the middle, the transition metals, they have varying charges, because we'll find out that they have in the shells where they keep their electrons, they have more places to put them than the other elements do. And so sometimes they arrange them in different ways. And so they can have different charges. Like for instance, cobalt can be +1 or +2. Copper can be +1 or +2. Iron can be +2 or +3. The only metals that aren't different is aluminum is always +3, zinc is always +2, and silver is always +1. That's it. Everybody else can change at varying numbers. So if we give the name of a compound, if I was to say copper chloride, that's not enough information, because you don't know what the charge of copper is, and so you don't know how much chlorine it's going to take to balance it. But when we go back to, so now we have lead 2 oxide. Because it's a transition metal, I need to tell you what the charge of lead is, because it could be a lot of different things. And chromium is a class. Chromium has at least 6 different charges it can be. So chromium's kind of crazy that way. So lead 2 tells us that that is lead +2. That is the ion it forms in that compound. And we also know that it's an ionic compound because it's lead, that's a metal, and oxide. What's oxide? What element are we referring to there?
Oxygen.
Oxygen, indeed. And so
Oxygen
do we remember what the charge on oxygen is? Remember, it's just above sulfur, and we determined that sulfur is in group 6 and has a charge of -2. Oxygen is just above it in the same group. So what do you think its charge is going to be?
-2.
Same thing. It's going to have the same charge. And so if I have lead with a +2 charge and oxygen with a -2 charge, what's my formula going to be?
PbO.
Yes. Yeah. Now, if you crisscross this time, you would get Pb2O2. But you don't need 2 to balance the charge. You just need 1. So it's just PbO, lead oxide. The last one is a trick question. Elemental fluorine. Elemental fluorine means that it's not an ion. And so we can't say it's F-. Fluorine and all the other halides, let me go back to the
F2
P table. So the halogens is the last group before the noble gases, group 7 or group 17, depending on how you're naming them. So it's this group here. And they all have 7 electrons in their outermost shell. Fluorine has 7, chlorine has 7, bromine has 7, iodine has 7. So they all need just one more electron to get to chemical nirvana. And so they all steal one electron and become chemically inert. They become chemically stable. So they all have +1 or -1 charges, all of them, when they're ions. Now, if we go back, we'll see that this is elemental fluorine. So it's not an ion, so it doesn't have a charge.
F2.
But yes, man, again, you should be teaching this class. So it can't be F. It can't be F because F by itself is super reactive and will form a compound with something, anybody. So what happens with F is with fluorine or any of them, actually, it forms a compound with another fluorine. And so elemental fluorine is F2. That's how you would find it. That's its most stable form. And we'll find out that chlorine is Cl2, and iodine is I2, and bromine is Br2, and oxygen is O2, and nitrogen is N2. Do you see a pattern? Almost all gases, with the exception of the noble gases, are these diatomic compounds. And we'll go over how we form those a little bit later. But for the rest of these, we'll work on them in class. We'll go over them in class as well, because we haven't really got to these yet. So 4 is just going the other way. Gives you the formula, and then you give it the name. This was actually a little bit easier than going from the name to the formula. And then let's just do let's just do one of these, and then we'll do the last one, and we'll call it a day. How about that? So this is just like the very first question. We just need to figure out, in addition to the element based on the atomic number and the mass based on the atomic mass, what's the charge based on the relationship between protons and electrons. So let's look at the second one. So
The ion 50.
So it's an ion, so we know, so we know it's got a charge. Oh, go back. There we go. So we know it has a charge. It has 54 electrons, 53 protons, 74 neutrons. So the first thing we need to figure out is, what element is it? So what element, how do we figure that out?
History.
It's what? How do we figure out which element that is?
There are 53 protons. It's 53rd element. That is.
Yeah,
that
so it is an
is
atomic number of 53. So which element is that?
Iodide?
Is it iodide? Iodine?
Iodine.
Okay, iodine.
iodine, yeah.
Okay. And remember, where does the 53 go? The top or the bottom?
Top.
Left or right?
Left.
Goes on the left-hand side, top or bottom?
Top.
Bottom. We put the atomic mass on the top. So it's 53 protons. So what's its atomic mass?
53 plus 74, which is 180. 28. So.
Yep, 128. So we put the 128 there. Now, what's the charge going to be on iodine?
No, not 128. Someone calculated.
127. Duh.
127.
127. Oops. Yeah, 127. So what's going to be the charge on iodine?
-1.
1.
-1, not +1. You always have to have the if there's more electrons, it's negative. If there's more protons, it's positive. So there's one more electron than protons, so we just put minus there. You can put -1 if you want, or just the minus. It makes no difference. If you just have the minus, it's assumed that it just means 1. So yes, and so iodine, like all the other halogens, so fluorine, chlorine, bromine, they all have the same charge because they're all in the same group. So iodine will always be -1. So we have the mass here, the number there, and the charge up here. Okay.
Okay. Excuse me.
Yep.
I've noticed that you write negative charge like -1, -3, like that. But when I was learning that, I was like writing 3 negative, 1 negative, like that.
Yeah, that's fine.
Okay.
Yeah, that's just you know, wherever you grew up, wherever you were. Yeah, a lot of people do 2 negative, 3 negative. That's fine. Yeah, that's an accepted way of doing it. I think the Western way of doing it is that the charge first and then the number second. But either way is fine.
Okay.
Yeah, they're both legitimate. As long as you have the number and the right charge, you're good.
Okay.
Right. Then finally, I don't know where 6 went, but 7 is here. I'll just sort of give you get you started with this one. Okay. So when we're dealing with different isotopes, we have to take into account how abundant they are. Just because carbon, let's say, where's carbon? Carbon has 3 basic isotopes: carbon 12, carbon 13, and carbon 14. You're probably familiar with carbon 14 because that's the one that's radioactive, and we can use it to date different materials because it has a very precise half-life. But when we consider the average mass of carbon, we don't just add 12, 13, and 14 and come up with 13. This isn't the average mass of carbon, isn't 13. Why? It's because almost all of carbon is 12, and a smaller amount is 13, and a really small amount is 14. So we have to take into consideration the abundance of each one, because if one particular isotope is super abundant, the average mass is going to be much closer to that one. And it's not always the smallest one. Sometimes it's the one in the middle, or it could even be the largest one. So we need to use both the abundance and the mass to figure out what the average mass is. So how we do this is we take the abundance and the mass. So here we have 3 isotopic masses to deal with. One is 19.99, one is 20.99, and one is 21.99. So we take the mass and we multiply that by the abundance. So what's the abundance for the 19.99?
Wait a minute.
90.92.
Right. So what do we multiply the mass by?
0.9092.
Right. So we multiply this by 0.9092. And what about the next one? What's the abundance of that one?
0.26%.
So what do we multiply that one by?
0.0026.
0.0026.
0026. Right. we need to divide it by 100. And the last one, what's the abundance of that one?
8.882.
So what do we multiply that one by?
0.0882.
Yes. Now
Excuse me.
Yes, go ahead.
Isn't AMU means atomic mass means protons plus neutrons? So within one isotope, why there's 0.990?
Because the mass of a neutron is slightly bigger than the mass of a proton. Just but slightly bigger. You know why?
Why?
Because a neutron is a proton and an electron together. That's what a neutron is.
Oh.
And we know that because one of the particles of radiation is an electron. It's called the beta particle, and it's basically just a stream of negatively charged electrons. And we know that comes from the nucleus. And so that basically blew everyone's mind when they figured out that comes from the nucleus, because like they spent years and years determining that electrons are outside the nucleus. And then it's like, well, yeah, it turns out they're inside the nucleus too. So when an element emits a beta particle, it actually changes the element, because it takes a neutron and turns it into a proton. So every time you emit an electron, your atomic number goes up by 1. Okay. So you become a different element.
Okay.
Right? Learn something. I love learning things. So in this particular instance, this is one of the class. Oh, go ahead.
You have beta. Do you have alpha?
Yeah, alpha. We're not really going to talk about radioactivity.
Okay.
But an alpha particle is actually the nucleus of a helium atom, and it has two protons and 2 neutrons, and it has a +2 charge.
Okay.
And then gamma is just energy. It's not a particle at all. It's just super high intensity energy that goes right through you. Alpha particles, very easy. Just piece of paper will stop an alpha particle. They're not particularly dangerous unless you eat them. Beta particle penetrates a little bit further, but a gamma ray will just go right through you, like an X-ray. That's why they're particularly dangerous.
Okay.
Let me erase some of this stuff. So
I can kill someone I hate with that.
I'm not gonna give you any ideas. So this is a classic example of where you should not round too quickly. So I would use all of the numbers like possibly can. So what's 19.99 times 0.9092? What number do I get from that?
That is 18.174908.
So
18.174908.
4908. Okay. What about the second one?
Second one times 0026. That is 0.054574.
4574. And the third one?
And wait, 0882. That is 1.939518.
Let's see, 1935.
395.
395.
Sorry, 1.939518.
Oh, 9. This will just start over. Okay, 1.9. Keep going. 3.
9, 5, 1, 8.
1, 8. Now, just go ahead and add all these numbers together.
20.169.
20. Keep going. 21.2016.
20.169. Oh, no, Professor.
20.169.
20.169. Oh, right. That's not all the digits, though. Give me all of them.
That's all.
No, you
That's
got
all
all.
actually. When I add it by the calculator, I add the same thing, and that's what gave me.
Okay. So it was 20. Give me the last three.
169.
169. So remember, when you add numbers, you go by how many numbers past the decimal you can use, right? So rather than just the total number of significant digits. So there should be 4 digits here, 2 here, and 3 here. So basically what we're dealing with is that we're going to be left with 2 digits past the decimal place. Because instead of reducing down to 2, because that's the smallest number of significant digits, no, it's how many digits past the decimal, because we're adding. That's the crucial. And so we can go 2 digits past the decimal. So what should our final, it doesn't, and so here's our 2 significant digits here and our 3 significant digits here. So you can see that we're fine with 2 digits past the decimal. So what's our final answer?
20.17.
Yes. We're not done yet. That's just a number. AMU. Yes, atomic mass unit.
Atomic mass unit.
Yep. So someone had a question.
Oh yeah, sorry. Where did you get the 4, 2, and 3? Is that how many?
Significant digits. So there are 4 significant digits in the abundance for the first isotope. There's only 2 significant digits for the second one, and there's 3 significant digits for the third one. But since we're adding, remember when we're adding, it's different than when we're multiplying. When we're multiplying, whoever has the fewest significant digits, that's what you're stuck with. But when you're adding, you go with how many digits past the decimal can I use? And you look for the one who has the most significant digits, and that is the first one. And so we have 1, 2, 3, 4 significant digits. So that means we can go 2 past the decimal, no matter how many significant digits the other numbers have. And so we'll report 4 significant digits. Hey.
Is that a dog?
Yeah, I got 2 of them here. Yeah, they're playing. So
I mean, is there a dog pacifier? What's that called?
Yeah, I could give them both. I could give them both a ball, but then they'd just be fighting over that. So
there's a pacifier for baby. I don't know for dogs.
Yeah, it's called a bone. I could just give them both a bone. I need to get them a bone. Okay, so like I said, the other questions, we're going to be dealing with those in lecture next week. So if you need more time to pass this one in, I totally understand. Not a problem.
Someone asked question on the chat.
Yes, what is it?
After we are done with this problem, can someone ask him to briefly explain problem 4?
Number 4, sure. Let me go back. 4. Oh, that's just the names. Okay. Let me get rid of these. So these are just different chemical molecules, and we want the name. So let's do one. Let's do this. Let's do this one. So you look at it and you see what it has in there. And so it has a metal and it has a non-metal. This is going to be an ionic compound. Like I said, we're going to get to this next week. We might as well get a little head start on it. That's an ionic compound. And so it means we're going to have a metal, and we give the metal whatever the name of the metal is, followed by the non-metal with "ide" at the end. So what's Mn? Anyone tell me what Mn is? Manganese. Yes, I did a lot of work on manganese in grad school, so I remember manganese. So that would be manganese.
Mhm.
Now, is manganese a transition metal?
It's supposed to be.
Yeah.
It is, right? So we don't know what its charge is. So we don't know what to put there. But we do know it has 2 oxygens, and we do know what the charge is on oxygen. So what's the charge on oxygen? And oxygen we're going to call oxide, right? It's oxide, O2. So what's the charge on oxygen?
2 minus.
Always, always -2. Always, always, always. And there's 2 of them. So what's the total negative charge?
Total negative charge, -4.
-4. So my total negative charge is going to be -4. What's my total positive charge have to be?
Plus 4.
+4. It's got to be +4. And there's only 1 manganese atom. So what has to be the charge on manganese?
+4.
Got to be +4. So we would put 4 there. So the name of that species is manganese 4 oxide. And that tells you everything you need to know. It tells you what the charge is on manganese. You already know what the charge is on oxygen. And so it tells you that it has to have 1 manganese and 2 oxygens in order to balance the charges. Now that is different from this one. What's different between this molecule, manganese oxide, and this one?
Laughing gas.
That is laughing gas. That's right. What is the difference between them?
Nitrogen is not
Not a metal.
metal. Yeah.
Not a metal. And neither is oxygen. They're both non-metals. And so because they're non-metals, this is not an ionic compound. This is a covalent compound. A covalent compound means that they're sharing electrons rather than forming ions. So there's no ions here. And because there's no ions here, they can arrange themselves in all kinds of crazy ways. So with a covalent compound, you just can't go based on what the charges are to figure out the number of atoms. In an ionic compound, it's easy. If I know what the charge of the metal is, and I know what the charge of the non-metal is, I can figure out how many there must be to balance. In a covalent compound, they can share electrons in all kinds of silly ways. I don't know. And so, like for instance, SO4 is a polyatomic ion with a charge of -2.
Mhm.
SO3 is a polyatomic ion, also with a charge of -2. How can that be? There's like different numbers of oxygens, but it's the same charge. And so because they're sharing electrons in different ways. Now N2O, none of them are ionic. And so we just can't say nitrogen oxide. That's not enough information because we don't know how many nitrogens and we don't know how many oxygens. So in this particular situation, we have, in a covalent compound, you have to name how many. And instead of using a number, we use a prefix this time. And so we would call it di for 2. Nitrogen oxide.
I think there's something called nitrous oxide.
Yeah, that's the same thing. That's the shorthand name. The proper chemical name is dinitrogen oxide, and then the short name is nitrous oxide. Mm-hmm.
Okay.
Yeah, so that's why CO is called carbon monoxide, and CO2 is dioxide. Because just saying carbon oxide is not enough information. We don't know which one you mean. It could be monoxide. It could be dioxide. It's a covalent compound. So you have to say how many atoms there are of each one before we know what it is.
So why not dinitrogen monoxide?
Yeah, I mean, you could, yeah, that's true. You could also call it dinitrogen monoxide. Yeah, you could call it that as well. Yeah, that's a good point. You could also call it dinitrogen monoxide.
Could we do the one, it's like
Which
calcium, and then I
with the one with calcium?
bromide, yeah.
Okay. Yeah, that one we'd have to look up.
Thanks.
So I can't remember. Yeah, so BrO2. One of the things that oxygen does is oxygen's super reactive. It basically bonds with everything, and you'll find that a lot of the polyatomic ions have oxygen in them. In fact, there's a whole series of them what we call oxyanions. Like, and they all have different names, like phosphate and sulfate and bromate, and there's all sorts of different ions, and we sort of give them, the root comes from whatever elements in the middle, and then we call it ite or ate, depending on how many oxygens there are. We're going to get to this a little bit later. So BrO2, bromine's in the middle, so we call that brome-8. So look up, I do not remember what the charge or the name of BrO2, because I think BrO4 is bromate. That might be bromite.
It's bromite.
It is bromite, right?
Yeah.
Bromite, ite means there's one less oxygen than the most. The most you can have is 8. So I think bromate would be this, and then bromite would be that, and then hypobromite would be BrO. So this is, we call that bromite. Bromite. So what is the charge on bromite?
Charge of bromide is +1.
Nope.
Oh no, -1. Sorry.
It's got to be -1. Why? How do I know it's -1 without even looking at it?
Because calcium is +2.
Right. Calcium is always +2. Always, 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 always +2. And so we don't have to write calcium 2. We never have to do that because it's assumed if it's a calcium ion, it's +2. So we don't have to do that. So we would just call that. So if we don't have to put the charge on calcium, what do we call this particular compound?
Calcium bromide.
Calcium bromide. You're done. Yeah, because calcium bromide. That's it. Because we know the charge of calcium is +2, and we know the charge of bromite. The fact that it's called ite means it's a polyatomic ion. There's the polyatomic ion, and we know what the charge is. So we don't have to give any more information. That's it. That's the whole name.
Excuse me.
Yep. Yes.
How do we name water? Dihydrogen oxide?
Dihydrogen monoxide. Yep.
Okay. Is that the name of the water or
no? Nobody calls it that. It's just water. No, nobody says that. Nobody calls it that.
Okay.
But if you want to, yeah, sure. I mean, it's nobody says it, but you wouldn't be in trouble if you did. Well, you would be in trouble. You'd look like a nerd. Oh, let's do the one just below it. Let's do the one just below it. That's a little bit of a trick. So I have, what kind of compound do we have here?
covalence?
It's covalent. Why do you say it's a covalent compound?
Because both S and O are non-metal.
Right. Both sulfur and oxygen aren't metallic. They're non-metals, so they will be sharing oxygens. They're not forming ions. So, but it's important to know that because SO3 is also an ion. If it's, I believe, -2, I think, or -3.
Yeah.
-2, I think. Yeah, sulfite. But this isn't sulfite because there's no charge. If there was a charge, it would be written here, but there isn't. So it's a neutral molecule. So it's a neutral molecule. There's no charge. It's covalent. So what do we call it?
Sulfur trioxide.
Yes. So we use di for 2. We use tri for 3. Tetra for 4, and penta
for
for
5.
5. Hexa for 6.
Hepta
for 7, octa for 8. So we just say sulfur. We usually leave off the mono if it's the first element. We usually leave it off.
Okay.
Like we don't say monocarbon monoxide. We just say carbon monoxide. So we call it sulfur. And that if we don't have anything in front of it, that just means 1. And then we put the tri on it because there's 3 oxygens. So yes, sulfur trioxide.
Is it like biology with the scientific names where you have to capitalize the genus and then lowercase the species?
No, all lowercase, unless you're starting
a sentence.
Starting a sentence with sulfur, then that would be a capital S. But no,
Okay.
all lowercase. Yeah.
Excuse me.
Mm-hmm.
Since the formula are easier, why we need names?
Because you need to go back and forth. If you find it beneath you, you can skip it, and I'll just mark it wrong. But we just have to be able to go back and forth. And there's things like this that there's things that they're easy to forget. Like once we've been dealing with these polyatomic ions for so long, you'll just look at something like SO3 and assume it's sulfate ion or sulfite ion and call it that, and it's not right. And then there's other things you need to remember. You need to remember to put the number in if it's transition metal. A lot of people forget that. And so there's things that are easy to trip up on. And then some people forget it's which compounds are ionic and which ones are covalent, because in an ionic compound you never give the number of atoms. That's only in a covalent. So a lot of people make that mistake too. Like this one, Na3P, they'll say trisodium phosphate or trisodium phosphide. That is not correct. So that's why we do it, because it's easy to trip up.
Okay.
All right. Any other questions before we call it? Man, we went to full 2 hours today. Good job.
Thank you so much, Professor James. I really enjoyed the class.
No problem. Oh, there's one more. Was there one more?
Acid.
Couldn't hear you.
Acid?
Acid?
The HNO2 one?
Yes, that's an acid. Yep. I'm not going to tell you which one.
Yeah.
Yeah. When you see, yeah, we'll get to that as well too. When you see an H in front of, we have a special name for those because they're not really ionic compounds, but they're not really covalent compounds either. So when you have a hydrogen in front of a nonmetal, we call that an acid. And
I mean, how to name acid?
Just call it hydro something acid.
Hydro,
Yeah, we'll go over it.
Okay.
All right. I will posts. I'll post all of the. Yeah, for some reason I submitted the lecture and lab to YouTube, but it didn't go in. So I'm gonna have to go back and do that over again, and then I'll have these posted by the end of tomorrow as well. Okay. Not that you guys need to. Well, could review it if you like. Anyway, I will see you. Have a good weekend. Try and get outside if you possibly can. Hopefully it won't get too smoky. And we'll see you on Tuesday.
Thank
Okay.
you.
All right. Bye, everyone.
Have a good weekend. Bye.
You too. Thank you.